Okay, we'll get started. Is there any questions about anything before we jump in? Okay, so we'll just pick up. Oh, it's not on the screen. So we'll try and wrap up the attack tree today. So if you remember, we were talking about HTTPS. Your goal as an adversary is to read the information that's going over the secure channel. We're going to assume that you're in a man-in-the-middle position in order to do it. And we looked at three sort of general strategies. One strategy was just seeing what you could see from outside the tunnel. Turns out you can see quite a bit. The second thing was to try and break into the tunnel. Today, the crypto is pretty secure. Wasn't always secure. There were problems historically with it, but a lot of those issues have been sort of ironed out. And then the third idea at a high level was to get the tunnel pointed at us. And then we don't have to break the tunnel because the tunnel ends at us anyways. And so we said, well, tunnels point at keys. Okay, so if there's a public key and you know the corresponding private key, you can get the tunnel pointed at you. And really the only job that your computer has in order to make secure tunnels to the right party is just trying to figure out, does this key belong to Concordia? Does this key belong to Google? You know, what's the mapping between keys and identities? Okay, so we have this whole certificate infrastructure. Certificate authorities like kind of just push the problem around. They don't really solve it. But anyways, we basically are living in a world where you buy a computer, it comes with a bunch of keys on the computer. These aren't necessarily the websites you're trying to reach, but they're authorities that will sign certificates for the websites that you're trying to reach. Okay? There's a lot of them, a couple hundred. And the reason that your computer can't, like your computer in theory could come preloaded with Concordia's key and all this thing, but websites are always changing, their keys are changing and things like that. So that's why your computer comes with these root certificates. Root certificates tend to last like 40 years or something like that. And so they don't change very often, okay? So that's why we have these certificate chains, is the things that are further down the chain, they can change more often than the root certificates itself. And then we also asked the question of, well, how does the CA figure out that Concordia's key is Concordia's key? And the answer is that it looks for Concordia to put something on their URL or answer emails that are sent to admin at Concordia or put stuff in its DNS record. Those are the basic approaches. And then we said, well, why can't we just do that? If a certificate authority they don't actually like have special knowledge about people's keys, right? They're just relying on DNS and other protocols. So why can't we just do it? And it basically just comes down to efficiency. So for me to do like send an email challenge and then get the response and then believe the key because I got the response, it's just too much for me to do when I'm connecting to a website. And as we've seen in many examples, when you connect to a website, you're actually connecting to 100 or 1,000, you know, like you're getting little resources from lots of different places and it's all getting weaved together. So you don't want to be doing 100 of those rounds of communication every time you load a website, all right? So that's why. But if you were able to stuff, certificate requests, or like basically, okay, I'll simplify it. If websites could just put their public key in their DNS record, then we would immediately have their key, because we have to go to DNS anyway to get their IP address. So then we grab their key at the same time. Then we don't have to have certificates or certificate authorities and all of that type of stuff. And so the question is, why don't we do it? Well, the answer is that the channel between us and DNS is not secured. So an adversary in this world would just wait for us to ask for the IP address and the key from DNS, and then it would substitute its own key in. Okay? Now, if we were able to get security on that channel, right, then we could start thinking about this. It turns out there's some other like subtle attacks around things like revocation and things like that, but this more or less would work if we had secure DNS. There are some proposals for secure DNS like DNSSEC, but they're not widely deployed for more or less efficiency reasons, I guess. Okay, so the high-level lessons of this sort of chapter about how CAs work and certificate authorities is, first off, certificate authorities, the word authority means like they know something. They're authoritative over that information. They're not really. Okay, they're not any different than you or I. Or if you want to start being a CA, you could send emails to admin at whatever the person who's coming to you asking for a certificate is. Okay, so they don't actually know anything. They don't know the companies. They don't know the people. They're not in a special position to say what people's public keys are. They just use a bunch of procedures that anyone could use. So they're not really authoritative in that sense. They do have experience. So they've been doing this for 5 years, 10 years, 20 years. Okay, so they sort of know where the pitfalls are and things like that. So that's one thing that they have that you wouldn't necessarily have is that experience. But they're not really truly authoritative. And then the other sort of high-level point is that usually when we think of secure tunnels, we think, okay, this is proper cryptography. It's hard cryptography. There's keys involved. You know, it's not like the world where we live in on the web normally where there's passwords and cookies and things like that. Okay, this is like, you know, full-length, full security keys that can't be broke by any computer. But when you look at the whole model holistically and you look at the whole issuing process, you realize that actually there's a lot of passwords that if you could just get the email password for a server, or you could get their DNS registrar's password, there's, you know, different ways of attacking the system, then you could more or less get any certificate that you want for that particular website. And so the whole thing kind of comes down to existing protocols working right, like DNS and HTTP, and it comes down to, you know, passwords and that type of thing, like keeping accounts secure. Okay. So if we start filling out our attack tree, here's a few of the things that we talked about. So what we could do is we could try to obtain a valid certificate. So how do we get the tunnel to end with us? Well, we just get a valid certificate, okay? And so we could subvert somehow the process by which certificates are issued. So it could be, if it's an automated domain validation, it could be the email-based thing. So we had a bunch of attacks. I won't go through them. Actually, maybe I will because it's been a week. So you could guess the password for the email account. You could intercept the email because email isn't generally, it's not sent with end-to-end encryption. There may be some kinds of encryption that are used, but they're at best sort of opportunistic encryption and not end-to-end, they're link-to-link. You could try and attack DNS, either the registrar or the DNS record itself. You could try to get a reserved email address like a min at domain. That might be hard to get, but sometimes a CA might use some obscure email address, like the example we saw was sslcertificates@live.com. If you can change, I guess this is related to DNS, so regardless of how you attack it, once you're into DNS, what you could do is you could change the record for the mail server, so now that email's coming to your IP address, your mail server, as opposed to the actual one. And you could do that by either stealing the domain, or you could do it by somehow, there are attacks on DNS itself, because DNS is a distributed system, and servers that don't know the answer for a DNS record have to ask other servers, and so there are other places that you can attack it. That could be a whole attack tree in and of itself, so we're not going to expand it further, but it's just sort of a node in our key. Okay. You could also do HTTP or DNS, and it's basically the same set of attacks. Okay. That's the automated verification. There's also these EV certificates. Notice that you don't have to get an EV. If you're an adversary and you want to intercept traffic, you can just get a DV. Okay, but if you want to get an EV or somehow it's easier, you could do some sort of social engineering kind of attack. Okay. We also talked about the fact that if you can attack any one certificate authority, there's 500 of them, then you can get, if you can either attack their issuance process or actually get their key, then you can create certificates for any website. Okay, so we know of that happening. What happens, the sort of backstory is Google obviously is they have a very popular browser, Chrome. They have a popular operating system on the mobile side, right, Android, and a maybe mildly popular operating system on the computer side in Chrome OS. They also have a very popular website, right? And so what Google did is they hard-coded the keys that they use, or at least the certificate authorities that they use. They hard-coded it in every copy of Chrome, Android, Chrome OS, okay? And what they did is they sat back and they said, will any of our users using any of our systems ever go to Google, the website, and see a certificate that's different than one of our actual certificates? And what they did is they added the functionality to Chrome that if it ever saw that, it would package it up and phone it home. So Google headquarters would receive a message saying, this user just tried to go to Google and they were presented with this certificate that's not on the list of certificates that you're expecting. So Google's able to do that because they're huge, right? Concordia couldn't do that, but Google can. And so once they rolled out that functionality, they indeed noticed that there were a bunch of weird certificates for Google that were floating around. Some of them came from a CA called DigiNotar. Some of them came from a CA called Komodo. This spawned an investigation. These CAs realized that they had been breached. And there were attackers out there that had fake Google, Facebook, Microsoft, like basically all the major, any major certificate that you might actually want. And they were going around and they were using this, and real users were seeing it, okay? Now, what do you do in that case? So Google now realizes it, right? We need a way to cancel a certificate or revoke it, okay? That's something that we'll talk about this lecture, so we haven't talked about how that works, but just keep that in mind. Certificate authorities, if you can't hack them or break into them, if you're a government, you might just go to them and say, well, by law, you have to give us certificates for Google and Facebook that we can use to intercept traffic, okay? And then another thing we didn't talk about is I mentioned that you do have this certificate root store that's on your computer. You can make edits to it if you want. So if you don't like a particular CA, you can delete it. It's just when you go to a website that uses that CA, then you're going to get an error, right? But there's nothing stopping you from just deleting it. Another thing you could do is you could add new certificate authorities. So if you wanted to be your own certificate authority, you could add yourself to your CA store or whatever, okay? Now, what happens is that some software will do this, okay? There's usually two settings for this. One setting is it's a corporate environment. So Concordia is giving me my computer. Concordia might make themselves a certificate authority on my computer. Now what they can do is they can intercept my traffic. Even if it's going over HTTPS, they see I'm trying to reach Google, they can just drop in, they can basically on the fly make a Google certificate that they signed, drop it into my connection, and now they can intercept my traffic, okay? So corporate software has this capability, but it does require your root store to have been modified, okay? The other place it shows up is if you have like kids or that type of thing, sometimes you have parental software. And so this is also, it's same idea, it's surveillance. Anything that goes over HTTPS, the parental software can't see. And so the parental software will often install a custom root certificate. Again, you need to get access to the computer. You're going to install it on the computer itself. But that's basically what it's doing, is it's actually doing a man-in-the-middle attack in order to intercept it. Then what happens is some security researchers, they went around to some of these big conferences like the RSA Security Conference, and they found that some of the people that make this software, they were selling boxes, and they were telling you that, hey, you take this box and you install it in your company, all the network traffic flows through it, you can intercept it, and you do not have to change anyone's computer. You don't have to install any custom root certificates, right? And so the security researchers were like, how's that possible, right? Like that doesn't work right. There's something wrong here. And so what they did is they actually bought one of the devices or somehow got access to it. They studied it. And what they realized is that actually one of these companies was able to become a CA. So somebody signed a certificate for them. And so they had like a certificate authority certificate on this hardware device, and it would just automatically generate certificates on the fly. And they were already trusted because they had a chain back to something that was in all users' root stores. Okay, so that's not allowed, right? They shouldn't have been able to do it. And once it became, like everyone became aware that it had happened, then the CAs that had issued the certificates for this purpose were basically kicked out of the. So in DigiNotar's case, I think in all three of these cases, they were all kicked out of the store, out of the root program. Komodo managed to stay, even though they got breached and they issued a bunch of certificates, they were considered too big to fail. So they just had too many high-profile clients that the browsers couldn't kick them out of the store. So they basically said, learn your lesson, and but yeah, it's shame on you, but we can't kick you out because it would break too many websites and it would just cause a big disruption in the market. So you can still see Komodo in the list of root certificates on your computers.
Did they update their certificate?
Yeah. So all the certificates got updated. Yeah. Okay, so questions about this portion of the tree? Okay, let's keep going. So this was a question that someone asked last class, and I sort of walked through it in words, but I'll show it to you. And the question was sort of like, maybe I'm mixing up my courses. I teach two courses. Someone asked about validation in a different context. Okay, no one asked this. But anyways, what is it when you get a certificate, you need to check it and make sure that it's valid, okay? And so it's worth pausing to think about, like, what are the actual checks that you're doing? What are you checking with the certificate itself, okay? So I go to Concordia, and I get the IP address from DNS, and I say, hey, Concordia, I want to talk to you over a secure tunnel. And Concordia says, good, I support it. I'll do a handshake with you. We'll set it up. Here's my certificate, and here's all the chain back to something that should be on your computer as a root certificate. Okay, so now I'm holding the certificate in my hand. Now notice the adversary's on the wire, so the adversary can do anything they want. They could drop a different certificate in or anything like that. And the promise is that the adversary could not drop a certificate in that was for Concordia.ca that wasn't a real certificate, because you can only Concordia can get certificates for Concordia.ca. That's the whole purpose of the certificate model. Okay. So what what you do every time you get a certificate, this is like a subset of the checks that you do, but it's the main ones. The first thing you're going to do is you're going to look at the CA. You're going to say, okay, this is signed by this CA. Was this CA in my root certificates, or was it signed by another CA, and eventually traces back to something that's in my root certificates? Okay, so you'll check that. The next thing you'll do is you'll check that the certificate you got is actually for Concordia.ca, right? I'm trying to go to Concordia.ca. Maybe the adversary has a certificate for evil.com because they legitimately own evil.com. They could just drop that in, right? And I'll be like, oh, that's a valid certificate. It is signed correctly, but it's for a completely different domain than what I'm trying to visit, okay? So I want to check and make sure that the domain that I'm visiting is the same, that the certificate matches it, or it covers that domain. I want to make sure that the CA certificates are actually CAs. Okay, so when you have a certificate chain, we didn't really talk about it, but certificates have a lot more. I sort of gave you the illusion that it just has a key and a domain, but there's actually a whole bunch of information in it, a bunch of crypto details and things like that. And one of the things that's in a certificate is there's a little flag, and it basically says, okay, this is a certificate for a CA. If you have that flag set, what that means is you can sign certificates for any domain, okay? But if you go to a CA and I get a certificate because I own Concordia.ca, I can't turn around and create a certificate for Facebook.com, sign it with my Concordia certificate. Technically, that traces back. I mean, everything is signed by something that traces back to the root certificate. But the certificate that I was given didn't authorize me to be a CA. Didn't authorize me to sign other certificates. It just authorized me to have a certificate for my own site. Okay? So the way that that's controlled is with this flag. It just says certificate authority, yes. So the root certificate in this chain the intermediate certificate in this chain, they'll both have this flag set as yes. And then the last certificate in the chain, the Concordia certificate, if you look at it, certificate authority will be marked as no. Okay? Simple thing, but it's something that you want to check. Okay? Now, certificates don't last forever. Okay? Nowadays, because there's a lot of security breaches and things like that, I think most certificates are about a year. You might be able to get one for 2 years. It might be more common to get something even 6 months. Okay? It used to be longer. You would see 5-year or 10-year certificates, but now all the certificates will basically last about a year, so you will have to renew it on a yearly basis. And then I've mentioned the idea, but we do need a way to cancel certificates because sometimes keys get lost. Okay, so that's called revocation. That's the fancy word for canceling a certificate. And so when I'm looking at this certificate, I also want to ask myself, is a certificate revoked or not? So I need to have a way of checking whether that is. Okay. So what I'm going to do is I'm just going to tell you some stories about each of these 5 things because there have been problems more or less with all of them. Okay, so the first thing I'll tell you about is an implementation flaw. So this it's like long gone now. It was back in 2014, but it was sort of an interesting thing that happened. So this happened on Apple, Mac OS, or whatever it was called back then, OS 10. And Apple has, the operating system has a SSL library called Secure Transport. And the flaw isn't in SSL itself, it's in the implementation of SSL. And so the flaw in this library was basically in the code that was doing these checks. Okay? So you have like 5 things that you're checking or 10 things that you're checking with the certificate. So that's where the flaw is in the code. So the way the code worked, just at a pseudocode level, is you had this condition called check. And basically it's a variable. It's going to hold 0 if everything's going well. And if you discover one of these checks and it fails, then you're going to set that to a 1. Okay? So if this ever gets a 1, then it's going to be considered failed. Okay? So the way the code progressed is you have an if statement, you do your check. So there's some condition, and assuming it passes, you would write a 0 into check. And assuming that it fails, you would write a 1 into check. Okay? Then you ask yourself, does check contain a 0 or a 1? Okay? If it contains a 1, I'm going to do something. And if it contains a 0, I'm going to also do something, I guess. Okay? So just based on this pseudocode, if check equals 0, what's the next line of code that I execute? So assuming that I do this condition, it writes a 0 into check. I ask myself inside an if statement, does check equal 1? Okay, it doesn't equal 1, it equals 0, so that's false. Okay, what's the next line of code that I execute? So there's 2 options. You could say I execute go to fail, or I could execute the next if check. Okay, so I'm going to go to the next condition. So I'm going to skip over it. So this line only gets executed if this condition is true. Okay, that's what an if statement is. Okay, now conversely, let's say condition 1 fails. Okay, then I now have a 1 sitting in check. My if condition is if check equals 1. That's now true, right? What's the next line of code that I execute? So I'll do the go to fail. Okay, now go to just means skip ahead. And so I'll skip way down to the bottom, and here's this fail. So I'm going to this last line, and then I'm going to return check, which will contain a 1. Okay, so the library that calls me will see that there was an error. Why do I skip? If condition 1 fails, why do I skip to the end? So the whole thing's going to fail anyway, so why even bother checking? Once one thing fails, then the whole thing's going to fail, so there's no point. Why waste time checking everything else? Okay? So let's say that this certificate wasn't signed correctly. I don't care about whether the domain or whether it was a CA, or there's no point in checking, it's going to fail anyways. Okay? All right, so that's the structure of this code at a very high level, like getting rid of all the complicated details. Okay? This code is fine. There's nothing wrong with this code, other than like go-tos are kind of not considered conventional. Like people don't really like them, but other than that, there's no problem with this. Okay, now Apple's secure transport code didn't look like this, unfortunately. There was an implementation error. It was a very, very small one-line error, and it was basically this. So somewhere in the middle of all of these checks, somebody copied and pasted go to fail twice, maybe on purpose, maybe not, we're not sure, but anyways. Okay, so what's the consequence of this? So let's go to this line here. We'll assume that this passed, so we're now on the second check. And let's say it fails. If it fails, check equals 1, we go to fail, which is normal behavior. What if the condition passes? So we pass the second check. We now have a 0 sitting here. Okay, why? Okay. So does the if statement apply to both of these lines, or does it apply to only one? Okay, if we had curly brackets after the if statement and the curly bracket ended after, then it would apply to both of those lines. In that case, there wouldn't be a problem. It's redundant to go to fail twice, but there wouldn't be a problem with it. The problem here is because we don't have curly brackets, this if statement will only either trigger this first go to fail or not, but it will always, all code that makes it past this if statement will go to fail. Okay? So all code will go down here. What does that mean about conditions 3 and 4? They'll never be checked under any circumstance. Okay, so it's we call it unreachable code. Okay, there's no way, there's no control, there's no path through this code where condition 3 and condition 4 get checked. What if condition 3 and 4 are very important things? Like, hey, does the domain of the website that I'm going to actually match the certificate that I'm being given? Then we don't check it, okay? Now what happens, what gets returned? So assuming I pass the first two conditions, then check is going to be equal to 0. Even though it's called fail, you're returning a 0, which says that you pass, okay? So this code, basically, as long as conditions 1 and 2 hold, then it will stop the check after looking at 1 and 2, and it will just report on the outcome of 1 and 2. Okay, 3 and 4 will not ever be checked. Okay, so this code is unreachable. And it turns out that, yes, this code did contain critical functionality with certificate checks, and it contained exactly what I said, which was the check that the domain that you were visiting matched the domain of the certificate that you're being provided. So what this means is that any user that was using this library basically had a Mac and was going to any website. What an adversary could do is if I have a certificate for evil.com, I see you going to Facebook. When Facebook responds with its certificate, I just substitute it with my evil.com certificate. It is a valid certificate because I do own that domain. It has my public key in it because it's my certificate. You accept it and you say, great, I just got Facebook's public key. It's the thing that's in this evil.com certificate, and you don't notice that the certificate doesn't match the website. Okay, so basically, it was trivial to man in the middle any SSL connection with any certificate. Okay, so just to wrap the story up, what can we do better here? So obviously, we don't want to write code that has this type of flaw in it. When this story came out, it was pretty big news because it was a pretty significant breach. And a lot of vendors came out and said, hey, we write static analysis tools. And we took Apple's code, which was open source, and we ran it through our static analysis tool. And lo and behold, it reported this. Therefore, Apple probably wasn't doing static analysis. That was the conclusion. But then other people came back and said, well, actually, it's true that your static analysis tool finds this particular flaw, but it also finds 10,000 other things in the code that aren't flaws. right? So this is the problem with static analysis, is that it does find the flaw, and everyone can point that out, but it finds lots of false positives that aren't flaws. And so the developer has to sit there and go through 1,000 things anyways to find the one thing that actually is a flaw as opposed to not being a flaw. So static analysis could maybe save you, but it probably wouldn't. The better approach would be what we call unit testing, where you write a bunch of tests, and your tests would include like just trying to connect to a website and getting the wrong certificate, like something that is a valid certificate, but it's for a completely different domain. You should fail that. Your library should not accept that connection. And if it does, then that tells you that there's a flaw. It doesn't tell you where in the code the flaw is, but you would see it right away. Okay? And so after this sort of became popular and people realized, wow, a big company like Apple could screw up and not catch it, I wonder what else is out there. And so then researchers, what they did is they started fuzzing all these SSL libraries where they would create weird certificates with all sorts of like weird characters and parsing errors and things like that. They would throw it at the library and just try and find, weird circumstances where it would accept something that it shouldn't accept. And they found a bunch of things. There's some research papers if you're interested in it. And of course, they're all fixed now, hopefully. But yeah. Okay. Okay, this is another story. So another story is you have a certificate. You are Concordia. You have Concordia's certificate. I mentioned, what if you just start issuing a certificate for Google? You sign it with your Concordia's key that's in your Concordia certificate. Okay? Because you're not marked as being a CA, if you give someone that Google certificate that you just issued, you have to give them the whole chain. So you'll give them the Google one, they'll give them the Concordia that signed the Google, you'll give them the global sign that signed Concordia, and the root certificate, okay? So it will chain back to a root certificate, but what the user will do is they'll check I don't care about the Google, that's the site certificate, so that doesn't have to be a CA, but everything else up the chain has to be. And so eventually they'll hit your Concordia certificate and they'll notice that flag wasn't set, and then they'll reject the chain. Okay, so that's what the code will do. And so this would be it would be up to the code to check this field, which is called basic constraints in the certificate. That's CA equals. It would be looking for it to be equal to true for all the actual CA certificates. Okay. It turns out that some implementations just weren't checking this field. So one example was Microsoft Internet Explorer. This is in the early days of the web, 2002, but it basically just never checked that field. Okay, so what that meant is, as an adversary, if you had any site certificate for any website that you actually own, you could just pretend you're a CA, issue another certificate using your site certificate as if it was a CA certificate, pass it to the user, and the user would accept it if they were running Internet Explorer. Okay? And so this was published, and then there was some tools that would let you do this. And then everyone said, oh, this is really stupid for Microsoft to have done, right? And like, shame on Microsoft, but like no one will ever do this again, right? It's too stupid. Like, we learned our lesson. It's such a basic thing to check. Now, like, no one will make that mistake again, right? Well, guess what? Apple said, hey, we want to get into this phone business. Okay, so we have this new device. It's called an iPhone. And by the way, we're putting a custom operating system on this iPhone, okay, iOS. It's not Mac OS or OS 10, which is on laptops. It's related to it. I'm sure a lot of the code is shared between the two, but it is its own operating system. And guess what? It's going to have its own SSL libraries and all these basic things written from scratch. Guess what they forgot to do? They forgot to check that all CA certificates were actually marked or flagged as being CA certificates. Okay? So again, you could do this exact same approach. And then that was extra embarrassing because Microsoft had done that like 10 years before. But anyways, now everybody knows no one would ever do it. If you're writing an SSL library from scratch, first off, you shouldn't. You should use some existing software. But if you were to write one from scratch, you would never make this mistake. Well, then a bunch of IoT devices came out. And these IoT devices connect to the internet. Therefore, they need HTTPS. Usually, I guess they could get by maybe with just HTTP. But, and again, a lot of custom operating systems, people just rewriting things from scratch, and they forgot to do these basic checks as well. All right, but it's not going to happen again, okay? 3 times. It happened in the 2000s, it happened in the 2010s, it happened in the 2020s, right? It won't happen in 2030 when we, I don't know, have a quantum computer that has a custom operating system or something like that. Okay, another thing you could do is, instead of, as an adversary, sweating the details of like, how am I going to get a certificate for, I don't control Google, I want to intercept Google traffic, I need a Google certificate, how am I going to get that? You know, even with all the sort of flaws in the CA system, how am I going to do it? What you could do is just say, forget it, I'm just going to drop in a certificate that's not signed by a CA. Okay? And I'll just sign it myself. It won't trace back to a CA store. I'll just drop it in, and we'll see what happens. Okay, so what happens if you are trying to go to Google and somebody drops in a certificate that's not signed by any certificate authority that your computer recognizes? Okay, you get some sort of error or warning in the browser. Okay, so the user gets it. So back in 2011, when some of these certificates were observed in the wild, this is what that error looked like. It said, there's a problem with this website security certificate. Security certificate was not issued by a trusted CA. Security certificate problems may indicate an attempt to fool you or intercept any data to you, blah, blah, blah. We recommend you close this website and do not continue to this website. Click here to close it, or click here to continue to this website. Not recommended. Okay? So you're just trying to go to Facebook. That's all you're trying to do. You're going to Facebook. You don't know anything about computers. You don't know what a certificate is. You don't know what trust is or authority is. You don't know about hacking. You don't know any of that stuff. You're just trying to go to Facebook. You get this warning. With one click, I can go to Facebook, which is what I'm trying to do, right? What are users going to do? Will any user click through? Well, is every user going to close this website? What should you do from a security perspective? Should be like, okay, no Facebook for me today, right? Until this like error goes away, right? As a percentage of 100, you know, like what percentage do you think of users would actually do what should be the secure thing as opposed to just clicking through? Who thinks more people would click through than close the window? Yeah, more people are going to click through, right? And so anyway, there were studies on it, and yeah, well over half of the people would click through. Sometimes they would report, I might click through. And this is in a lab setting where people are kind of primed to think about security. And so what they would actually do in real life like might be even higher. But basically, yeah, so lots and lots of people click through. And so that was the thought too, is that if you want to attack people, just drop in a certificate and have them click through. Okay. Now what happens is we've tried to improve, not we, but like researchers, like, so here's a paper from people at Google that work on Chrome. They spent a long time trying to improve these warnings to reduce the click-throughs. Okay. So this is what a modern click-through would look like. And there's basically two differences between what used to be the case and what is now the case. Okay? The first difference is that the language is extremely simplified. So in this case, there's lots of talks about certificates and security and servers, lots of technical jargon. Okay? Here, there's none of that. Okay? It just says, hey, your connection might not be private. Attackers might be trying to steal your information. Okay? So it's in very plain language. The second thing is first off, you only see this first box. I know there's this bottom bit. This bottom bit you only see when you clicked on advanced. Okay? But anyways, if you just look at the first warning that you're given without clicking on advanced, you're just seeing what's in the top box. There is no click-through option. Okay? The only option is back to safety, which basically says you don't go to the website. Okay? Now, if you want to, you can click on advanced. Now there's a more technical description of what's happening. And then there is a link that says proceed to it unsafe. Okay? So if it's a case where you're an expert and you're willing to take that risk, right, you can click through. They could just say, like, you can never click through. It's just not an option. Okay? So they still want to give the user the ability to click through if they really want to. But what they did is they tried to really improve. They tried to lower the click-through rate for things that would actually be attacks. Okay, so now you have to click advance and then click through. And then if you want to try it yourself, you can go to this website, which is a good website. We saw it earlier, Bad SSL, and it basically has all sorts of different errors. Some of these things we talked about, some of them we didn't, but you can see what your browser looks like under different conditions. So for example, let's say I was given a self-signed certificate in Safari, then this is the warning that I would get. So it very similar to the Google language. It just says the connection's not private. The website might be impersonating this real website to steal my information. You should close it. The only options here are close page or learn more about it. Okay, there's no click through. All right, but if I do learn more about it, then there will be, here again, it's not even like a button that's prominent. It's just a link that's sort of mixed into the text. But it says, if you understand the risks involved, you can visit this website. And then there's yet another warning, right? Now in this case, the warning is being triggered because the SSL is failing because the certificate fails. But then if I click through here, I eventually get to the website itself. Okay, so I can click through, but it's a lot harder to click through. Okay, here's a couple other like fun stories about things that went wrong with SSL. So what we were just talking about, one of the checks that you have to do is you have to check that the domain that you're visiting matches the domain that's inside of the certificate itself. Okay. Now, let's say that you go to a CA and the CA says, you say, okay, I want a certificate. Here's my certificate. I want you to sign it. All right. And I have to write the domain name for the certificate I want them to sign. Okay. So let's say I do something fun. Like I write in, I want a certificate for google.com nullcharacter.concordia.ca. Okay? That's not a valid string because it has a special character, which is this null character. Okay? No websites are allowed to have special characters like that in the URLs itself. Okay? So, but it's up to the CA to decide what to do with this string. Okay? And it's not a human that's looking at it saying that looks weird. It's software. Software is going to look at this string and try and figure out what to do. And maybe the person that wrote that software wasn't anticipating that somebody would give a string that looks like this. Okay? So put yourself in the shoes of software, not a human, and you see a string like that. What would you do with a string like that? Okay, so option one is you can reject it. Okay, crash or just say invalid string, throw an error, don't accept it. Okay, that's a great option. Is there anything else that you could imagine software doing instead?
I could just remove it and then take the rest of the...
Okay, so another option is you could just remove it. You could say, I don't recognize that character. It's not a valid character. I'm going to skip over it. What's the domain in that case? If you skip over the null character or drop the null character. Okay, so the domain is google.com.concordia.ca. Who owns that domain? It's a weird looking domain, but like who is that Google's domain or is that Concordia's domain? That's Concordia's, right? It's just a subdomain of Concordia. You can have images.concordia, mail.concordia, google.com.concordia, like whatever you want to do. You can do what you want, okay? So that's some weird looking subdomain, but it is a subdomain. And sometimes you see this in phishing, right? They'll do things like google.com and then the real domain because they can't get control of that domain. But if the first thing your eyes see is google.com, right? Then you're thinking, oh, this is a Google website, and you don't necessarily notice that it's followed by a dot as opposed to a slash. Okay. Is there anything else software might do? So you can reject the string or you can drop the null character. Anyone program in C? Okay, so it could parse them out and split them out. So that's not an option that I have here, but that's another option. And there's one other thing it could do, particularly in C, if you were to pass this in as a string. Say it loud. It's not exactly. Yeah.
Would you try to decode it in some other format?
So you could too as well. So that's not what I'm thinking of. Okay, so if I'm programming in Java and I have a string, how does the Java virtual machine know that this is supposed to be a string? Okay, so Java in this case is typed, and so there'll be some envelope that basically says this is a string. Okay, so Java knows it's a string before it even starts reading the string itself. Okay, C, much more efficient language. We don't want all these envelopes and identifying, typing data types and things like that. What does C do? They say, well, if you're interpreting it as a string, then it's a string. It might not be. It might be an image. Well, then you're just going to get the image in terms of a string. Okay? So you read it. You say it's a string, fine. Just start reading. Okay? So you point at the first character, G, and you start reading. Now, when do you stop? So also in Java, they'll say this is a string and this is how long it is. All right? In C, you don't know how long it is. You don't even know it's a string. You're going to start reading. Eventually, you got to stop. When do you stop? So when you hit a null character. Okay, so this is called a null terminated string. It's just something that C does. And so you don't even know it's a string. You just start reading. If you hit a null, you stop, and you're like, that's the end of the string. Okay? So imagine your software, you're looking at this domain, and you're deciding, and you're written in C, and you think this is a null terminated string. What's the domain that you're looking at? Google.com. And who owns Google.com? Between Google and Concordia? Google, okay? It's an obvious question, but anyways. Okay, so depending on how you parse this, if you reject the string, then that's fine. The certificate doesn't get signed, okay? But if the CA drops it, it's going to say this is a certificate for Concordia. And if it null terminates, it's going to say this is a certificate for Google. Okay, so they're two different entities, depending. Okay, now you as the person asking for the certificate are either Concordia or Google. Okay, so the fact that it could be parsed different ways doesn't actually help you. Doesn't let you get if you're Concordia, get a certificate for Google or vice versa. Okay, it's going to be parsed one way, and if it's in your favor, you're going to be able to prove that you're Concordia, but you're not going to be able to prove that you're Google. Okay, so where's the security problem? So the security problem is when you have different people that do different things, and in particular, when the CA that signs the certificate is doing one of these things, and the browser that the user is using is doing a different thing. Okay? Because once you get your certificate signed, then you're going to give it to users. Users are going to do the check of the certificate in their browser. All right? And so their browser might look at that string differently than what the CA looked at. Okay? Specifically, if the CA drops the null character, it will say that this is a Concordia certificate. It will do the test with Concordia, and assuming you actually are Concordia, you're able to satisfy that test. It will sign the certificate. When it signs it, this is just a minor detail, but when you ask a CA to sign something, you actually give it to them and they just put their signature on the end, as opposed to you saying, I want a certificate for this domain, and then they fill in that field. So what that means is because you're giving it to them with the null character, they're signing it with the null character. So that null character makes it into the final certificate. Okay? Just when they pulled it out, they dropped the null character, but it's still sitting there in the unsigned certificate. Once they're satisfied that they're able to issue the certificate to you, they sign it with the null character intact. So now you have a certificate not for concordia.ca or for google.com.concordia.ca. You have a certificate specifically for google.com.null.concordia.ca. Okay? And you can give that to any user. And if you find a user whose browser is going to null terminate this, that user is going to think you just gave them a Google certificate. And it has your key in it. Okay? So then you could use that to man in the middle their attacks. Okay, so the problem is when the browser does 2 the CA does 2 and the browser does 3, you could flip it as well. So in this case, you would flip the order of these as well, but you could do it in reverse if the CA was going to terminate the null character and the browser was going to drop the null character. Okay. So parsing is really important, especially when you have different libraries written in different languages, operated by different people, and they're all supposed to look at something and parse it exactly the same way. You can find other flaws in what's called the X509 standard, which is for certificates, where different things go wrong when you do weird things, and the adversary will do weird things, right? Where different libraries will parse things differently, and that mismatch can lead to problems. Okay, the final thing I want to talk about is revocation. So this is like what happens if I steal your key, right? And you realize I stole your key, or I trick a CA and I get a Google certificate even though I'm not Google. Google somehow figures it out, right? Now people want to cancel the certificate. They want it to be marked invalid, okay? So we got to do something about that. Okay, so let's assume that the adversary steals Concordia's certificate. So with that certificate, it can now intercept any traffic. It can end the tunnel. If the user tries to connect to Concordia, it can end the tunnel at the adversary, and the user thinks everything is fine. Okay, first off, Concordia can just go get a new certificate. So that's fine. So they stop using the old one that was stolen. They have a new one. No one knows the private key in their new one. Okay, but that doesn't actually solve the problem because the adversary can continue using the old one. Okay, so just because Concordia gets a new one doesn't invalidate the old one. So the user will connect to Concordia. Concordia will send its new certificate. The adversary will just replace it with the old certificate that it knows the key for. And then the user doesn't know that there is a new certificate to look for. Okay, so we need to explicitly cancel or revoke the old certificate. All right, how are we going to do this? Who's going to do this? Right? In this picture, who's it going to? So Concordia really can't do much because all the information they send to the user, they can say, oh, by the way, that old certificate is canceled. But if the adversary's in the middle, then they're just dropping that information. Okay? So if the adversary's in the middle, then Concordia really can't get the message through to the user that they shouldn't be using this old certificate. Notice that until the user looks at the certificate and validates it, they can't have a secure tunnel. So they can't send that information over a secure tunnel because they don't have it yet. They're in the pre-tunnel phase, the handshake phase of the protocol. Okay, so what we're going to do is we're going to turn to the CAs. So the CAs that issue the certificates, we're going to say, okay, you need to figure out some way of maintaining a list of certificates that are valid and invalid. All right? And so users need to be able to check that list. And so there's two main ways that this is done. The first one is that let me describe it a little bit different. Okay, the first option we call a status check, and it basically is every time you get a certificate, you need to go ask someone who's maintaining a list of valid and invalid certificates, is this still valid or not? Okay, so every time you do a certificate, there's an extra round of communication where you go and you say, I just got this certificate, is it valid? And you get back an answer that's either yes or no. Okay, now who are you going to ask? Well, it's in the certificate itself. So when you look at the certificate, there will be a field and there'll be a URL for a server, and this server will answer your questions about whether the certificate's revoked. And normally it's the CA that issues the certificate. They're going to be also the responder here. Technically, they could designate someone else to do it, but they'll do it for themselves. Okay, so this is what it would look like. So if you looked into a certificate, there's going to be this field called OCSP, which stands for Online Certificate Status Protocol. And there'll be a URL sitting there. And you can ping this URL and it will tell you, yeah, the certificate is valid or not. Okay? You can just send the hash of the certificate and it will respond. Okay, so let's say that you come out of this lecture saying this CA stuff sounds really easy. I just have to send some emails to admin at domains and then I can issue certificates. By the way, people are paying me hundreds or thousands of dollars for every certificate. That sounds like a really good business. And so you start your own CA. So that's great. Congratulations. And you sign up the biggest websites. You undercut everyone in terms of price. And so now Google, Facebook, Twitter, they're all your clients. Okay? What happens when you have to put up one of these OCSP responder servers? So you're going to put up a server and it's going to answer information about revocation. How often are people going to ask you about certificates? Is it going to be a little traffic or a lot of traffic? So basically, every time someone gets a Google certificate, they have to ask you whether it's valid or not. And even if they already asked you, they got to ask you again, because maybe since the last time they asked you, it's changed, right? Okay? So every time a user connects to Google, they're also connecting to you. Okay? Now, your job's a little smaller. You just have to send one message back, whereas Google has to serve up an entire website and deal with the user for a bit. Okay? But basically, your bandwidth, in terms of the number of users that are coming to you, is equivalent to the bandwidth of Google. Okay? So like every user that goes to Google, and now imagine you're the CA for Google, Facebook, and Twitter. Every time any user anywhere in the world goes to that website, they're also coming to you and asking for a certificate check. Okay? So you have to have a huge infrastructure, right, in order to handle that traffic if some of your clients are big websites. Okay? Did CAs, do you think, have that big infrastructure? So they didn't. Okay, they were just rinky-dink organizations. They would sign these things. They would throw a server up, but if they ever landed a big client, they just couldn't handle the traffic. Okay, so OCSP servers traditionally were basically always down. All right, so what happens is you get a certificate, you go ask the CA, and you just don't hear anything. They don't say no, they don't say yes, you hear nothing back. Okay. So what do? Now you're a browser, okay? And technically what you should do, this is a failure, right? You were unable to check whether the certificate was revoked. It failed that certificate check. You have to decide on a certain window of time. Like, am I going to wait a second, a millisecond? Am I going to wait 5 minutes? How long am I going to wait? But eventually you're basically going to have to fail if you don't hear back from it, okay? Now, the problem with this is that there were so many CAs that had inadequate servers that if the browsers actually failed every connection through an error, through a warning, or just had the page hang while you're waiting for the certificate status check, then users would experience that with all websites, right? We would all go to Google and we would hang there for 30 seconds and then it would say error, unable to check, okay? And so it was just happening so frequently that what browsers decided is we can't enforce this. There's no way we can enforce it, otherwise the user experience is going to be terrible, okay? So what browsers did is they decided we're going to fail open, meaning we're still going to try and do the check, okay? We will send the message to the server. If we get a response yes, then we go ahead. If we get a response no, then we will throw an error because the certificate has been revoked, okay? But if we don't get any response at all, we'll wait a little bit, but then eventually we're just going to load the website and pretend that nothing happened. Pretend that the certificate was valid, okay? Now you're a man in the middle. You're this person, and you have the old certificate. The website's trying to send the new certificate, and on top of that, the old certificate has been revoked, okay? Does this picture work anymore? So the user connects to Concordia. Concordia sends the new certificate. I drop in my old certificate. Now the user is going to turn around and go to DigiCert or whoever and say, is this certificate I just received revoked or not? And the answer is going to be yes, it is revoked. Okay? But what can the adversary do if they're on the wire between the user and the certificate authority. Okay, so they could try and change it, so they could flip the answer. So one thing you might notice is this going over HTTPS? It's going over HTTP. Okay? All right, so we'll come back to that. What else could they do that's even simpler? Other than going in and actually manipulating the message, they could just drop it, right? So the CA will say, yes, the certificate's revoked, and then they just drop it. The user waits a while. They're not hearing that it's revoked or that it's not revoked, and so they say, well, the server must be overwhelmed, so I'm just going to connect anyways. Okay? So basically, revocation doesn't work. Okay? Okay, now back to this issue. Why do you think they use HTTP? That seems kind of crazy. It could be like it doesn't matter anyway because the adversary can just drop it. Okay, but there's another reason why. Okay, what would happen if they use HTTPS? Let's think about it. So I go to Concordia and I say, I want to talk to you over HTTPS, and it says, great, here's my certificate. I open up the certificate and I say, oh, I don't know, is this revoked? So then I go over to Global Sign and I say, what's the first thing I say? If this is over HTTPS, the first thing I say isn't, is this certificate revoked? Because I have to set up my HTTPS connection to them, right? So the first thing I say to them is, hey, I want to talk HTTPS. Then Global Sign says, great, here's my certificate. Then I'm like, oh, is this certificate revoked? Right? So then I go look up some other HTTPS OCSP responder, and I go there and I say, oh, hey, I want to talk HTTPS. And they say, great, here's my certificate. And then I say, oh, I wonder if this certificate's revoked. Okay? So basically, you can never complete. You end up in an infinite loop where you keep getting certificates, right? And you have no way of checking them because every certificate requires you to form a secure connection somewhere else. All right? So that's why you can't do HTTPS. So you have a circular dependency. So what that means is that the adversary could also change the response as well. Okay. Now what CA started doing is, even though it's not over HTTPS, is they'll sign the certificate response. Okay. If they sign it, then it's fine. It's not being signed within the HTTPS protocol. It's being signed on the packet itself. But the adversary can still drop it. Then what browsers did is they started saying, remember these like DV, EV certificates? What we're going to do is we're going to start requiring stricter standards for EV certificates. And one of the stricter standards is that your OCSP needs to be online at all times. Okay? And if it's offline, then we're going to, I don't know what the consequence is, we're going to revoke you or things like that. Okay? Then eventually, CA started putting in proper infrastructure, and so they were able to handle it. And then once they were handling EV traffic, then now the browsers are basically saying you need to turn it on for everything. And so I don't know the current status of that, if it's actually deployed for all DV certificates, but it's in some stage of rolling out where you more or less can now get revocation responses over OCSP. Okay, the other thing that you could do is the CA will sometimes just publish a list of all revoked certificates. They'll sign it and they'll publish it. Okay? Now, what's the difference between the two? Well, one's like a real-time check. And with the real-time check, I'm only checking the website that I'm going to Concordia, I have my Concordia certificate. I don't care about all the other certificates that you issued. Okay? I just want to know for this one certificate. Okay? So it's a very narrow request, but it is an online thing that requires a response. With the CRL list, I get a big list that involves all sorts of certificates that I don't care about, and I just care about whether my certificate's on that list or not. So it's sort of like a bigger data structure. It's not a personalized request, but you don't necessarily need a server that's online 24/7. You could distribute it. As long as that list can somehow get to the user, then the user can check it. Okay, so what browsers, starting with Chrome, did is before they cracked down on OCSP response rates. They actually got to a stage where they just turned it off completely, and they said, what we're going to do is, we as Google, the company, are going to go around to all the CAs. We're going to ask them for their CRL, their revocation lists, and we'll put it in a format and we'll send it to our Chrome users. So your Chrome browser will just sort of automatically, I don't know how often it happens, let's say it's once a day or something like that, it will go and it will fetch from Google the latest CRLs, which Google themselves curated from all the CAs, okay? And all users have the exact same set of revoked certificates. So this is called a CRL set. The problem with it is, at least this data is like very old. I don't know that someone's done it recently, but at least at the time, the percentage of CAs missing from the CRL list was like 75, 85% kind of thing. And so it's a good idea, but it wasn't actually that broad in terms of its coverage. Then there's another option, I guess, a third option, and this one makes a lot of sense. This is probably the most sensible one, which is you go back to OCSP. So like you ask the CA, is this certificate valid or not? And it says yes or no. But instead of every user that, say, goes to Google going and asking, Google goes and asks. They get the response signed, time-stamped, and then they send it to all their users. So they say, here's a certificate, and 5 seconds ago I asked the CA whether this is revoked or not. They say it's not revoked, and you can see that it was signed by them and it's time-stamped for like 5 seconds ago, okay? And so now you have everything you need as a user to check its revocation status, and you don't have to ask the CA themselves, okay? So that idea is great. It actually works very well. The problem is, where do you stick that extra information? You now have this extra data, and it's in this HTTPS protocol. You have to put it somewhere, okay? And what happened is, what they realized is when they turned it on, I think Google experimented with it so they would turn it on, is that there would be some packet inspection happening in the middle of the internet in some backbone server, and they were like looking at these packets, and there was this extra field and they didn't know what it was, and then they were just dropping them or throwing an error or something like that. I forget what the exact consequence was, but basically the packets weren't going through. And so it was considered not reliable enough. You want things that are 99.999% reliable. It wasn't reliable enough, and so it never was deployed. But in the future, if these protocols get overhauled completely, then that might be an option. But anyways, so where we are today is that now there's a lot of pressures on CAs to make their servers work, okay? So the pressure is on you to go back to option one, but this time with proper infrastructure. And so that's probably where we'll end up. But again, it's sort of in flux at the moment. Okay, another option you could do is, so I call this use no certificate. That might sound like you use like a self-signed certificate, or you use a certificate where it doesn't trace back to a proper CA. In this case, what I mean is you could try to not do HTTPS at all. So let's say that the user is trying to connect to Concordia, and you want to intercept it. If you can keep them on HTTP, then you have no problem intercepting their traffic, okay? So then we have to stop and pause and think a bit about, how do you end up on HTTPS in the first place, right? So there's different ways that you might end up. One of them is a redirect. So you would connect to Concordia over HTTP. Concordia would say, oh, whoa, I talk HTTPS. It sends that back to you as a 403 redirect, and then your browser will say, okay, now I'm going to go connect to HTTPS, okay? The problem is, because that interaction happened over HTTP, if there's an adversary in the middle, they can just drop that reconnect, okay? They can just say, oh, actually, I'm happy to talk to HTTP. Send me your data. So you send it over HTTP. They can then form a HTTPS connection to Concordia and drop your information and basically relay it back and forth, okay? So So that would be one thing, would be the redirect. Okay. Another thing that was very, very common that we all like wised up to, so this attack doesn't work anymore, but it was another thing in the history of HTTPS, is there were a lot of websites, and what they wanted to do is they wanted to use HTTPS for like the minimal amount of time possible. And I think the thinking behind it was because you have to encrypt and decrypt data, that it's expensive to serve things over HTTPS. So if we can serve stuff over HTTP, that's fine. We understand that if you put a username and a password or a credit card number or something like that, we have to take that over HTTPS. That's fine. We'll redirect to HTTPS for that purpose. And then as soon as I got your password or credit card, we'll flip back to HTTP. Okay, so that was the sort of mentality for a lot of websites. So it was very common that you would go to a website and it would come to you over HTTP, and then there would be like a button, like a sign in. It might even ask for your username and password right there. You could type it right in on that website. Okay, now this website was coming to you over HTTP, so there was no lock. It was asking for your username and password. If you typed your username and password in and pressed the submit button, what would happen? Well, it would actually redirect to HTTPS. Okay? So that submit button would be wired to form an HTTPS connection. In other words, the HTML would say, grab the thing the user typed in, send it to this URL, and that would be an HTTPS URL. Okay, so that was the experience that you would have. Is you go to websites, it looks like it's not secure, there's no lock, but if you did type your password in and press enter, then the lock would appear on the next page because they switched over to HTTPS in order to accept that. Okay, now let's say that you're on one of these websites and you think it's going to work that way because every other website that you use works that way. Okay. But how can you know for sure that when I click that button, it will be sent over HTTPS as opposed to HTTP? So I can't look at the lock on the website itself because it doesn't have one. So that's out. What if there was a lock, like it had sign in and then there was a little lock icon beside sign in? Or say it said submit and there was a lock picture there. That means it's going to go over SSL, right? If there's a submit button on the website and there's a lock. Okay, even simpler, it's just an image on the website. It doesn't actually mean anything, right? So anyone can put any image on any website. You can put a lock anywhere on your website. It doesn't mean anything, okay? So the answer is there's actually no way to know, okay? Unless if you want to dig into the HTML of the page itself. So you could go into inspect element, you could find that sign in button, and then once you find it, you can see what URL it's redirecting to. Oh, it's going over HTTPS, not HTTP, therefore it's secure, okay? Are everyday users going to do that? They can't do that, right? That's unrealistic. You can't even really write like an extension, a browser extension. There was some research on this, like could you write a browser extension or something like that that would do this automatic? But every website's coded in a different way, and it's just a mess to try and do it in a way that would be easily recognized. Yeah.
But like as you said, the website actually is coming via HTTP, right?
Yeah.
So I as an attacker could still change this HTTPS to HTTP. So that would have been
Okay, perfect. So this website's coming down. You're an adversary in the middle. You see that this submit button is wired up to go over HTTPS. You know that if the user submits their password over HTTPS, you don't get that password, but you want it, right? That's your job as the man in the middle. So what do? You switch HTTPS in the HTML file to HTTP, send it to the user. Now the user has a page that looks exactly the same. Maybe they've used this web page 100 times. I use this every day. Every time I log in, it redirects me to SSL, right? Now this one time I get the website, it looks no different. There's zero change to it at all, unless if I were to go in and look at the HTML, right? And now I type my password expecting that it's going to switch over to SSL. I hit the submit button and it doesn't, okay? Now what do? Nothing, right? Like it's too late. you've already submitted it, your password's already gone over HTTP, the adversary has it. Okay, so you might recognize it after you hit the submit button. Most users wouldn't even recognize it anyways, but you might be like, oh, that's weird. The lock didn't come up after I submitted it, but it's too late at that point. Okay, so what you can do is you can run a little proxy, and you do have to modify packets. So as packets are coming by, it's not good enough to just inspect them. You do have to modify them, but it's a pretty simple modification. What you can do is basically say, go through this HTML file, and every time you see HTTPS, just replace it with HTTP. Okay? And all the links will still work, but now they're just going to go over HTTP instead of HTTPS. You can change them when the user comes back. You can change them as well back to proper HTTPS. So basically, the adversary can have proper HTTPS connections between themselves and all the servers that are being visited, but between the user and the adversary, it's all HTTP. Okay, so once you're on HTTP, basically, if you're being attacked and there's an adversary in the middle, they can keep you from ever leaving HTTP. You'll never get off of HTTP. You'll only go to HTTPS, or you'll never go to HTTPS. Okay, the only option you have as a website is you want to move your entire website. So none of this, like, I'm going to show you the landing page over HTTP, and then when I collect your information later, I'm going to ask for it over HTTPS. My choice is I just have to give you my entire website over HTTPS, only always over HTTPS. When it's in Google and someone finds me through Google, it's HTTPS. They click the link from Google, it doesn't go to HTTP and I redirect them. It just, Google knows that it's an HTTPS website. When the Google bots go around and crawl the web, they see that I only support HTTPS. Okay? And it just becomes known that I only support it, right? And there are other things, like you can set flags and things like that to say that you only ever support HTTPS. And so that's what you see now. So Concordia, for example, if you go to concordia.ca, the root page, it doesn't have any sensitive information, right? It's just advertising, marketing for the university, information, public information, but it's on HTTPS. Okay? So like the entire websites are on HTTPS. Wikipedia is entirely on HTTPS. Okay, one other attack. Let's say that you go to this website. So I go to a website and there's this pop-up window. Okay. Now again, this looks ancient because this example is kind of ancient, and browsers don't do pop-up so much, and it's actually for this reason. But anyways. But imagine a world where like a browser window would spawn a new browser window, okay? So I go here and I'm looking at this pop-up window for paypal.com, okay? I see that it indeed has a certificate. I know it's hard to see, but the lock is on. It's even an EV certificate, so it's green. It says this is PayPal, the company in the United States, okay? So this looks good. There's a username and there's a password. And so I type in my username, I type in my password, I hit the login button. Is that fine? Is that secure? Looks good, right? Now, I'll give you a hint. I probably wouldn't show it if it was secure. Okay, so there is an actual issue with this. Is there any way that the password that I typed in here doesn't end up in a secure tunnel to paypal.com and it ends up at the adversary instead? Okay, so let's just go through our reasoning. I'm going to ask you some very obvious questions, but just roll with them. So I hit this login button, right? Where's the password that's going for this login button? So it's going wherever this is wired to. We don't know. Again, that's buried in the source code. But it was who chose the destination for this login? Okay, so the HTML for this website itself. And where did I get the HTML for this website itself? Well, my connection is to paypal.com, right? So when you pop up a window, does the outer window get to specify what the content of the website, or it just passes a URL and says, go load this URL. So a pop-up will say, okay, go pop up a window at this URL. And so I look at this URL, okay, and it's paypal.com. There's a lock there. So the HTML in this website, like inside this, did come from paypal.com. Okay, including wherever PayPal. So PayPal might have a vulnerability in their website where they send my password somewhere stupid. I don't know, but anyways, the password, the HTML in this site came from PayPal.com because that's the website I'm on, right? In this pop-up window. Okay, is it the actual website I'm on in this pop-up window?
No, it's a mock-up.
Okay, how do I know that this is actually a pop-up? What does it mean to be a pop-up window? Kind of a dumb question, but what is a pop-up window?
Separate window.
So a separate browser window, okay? So like, for example, this close button and the star button and all this stuff, that's the browser itself. That's Internet Explorer, for example. And the content of the website is everything that's in the frame here, okay? So all the buttons and stuff that's put there by either the operating system or the browser, we call that the Chrome. That's actually where Google Chrome gets the name, but that's called the Chrome of the browser. So windows are distinguished by their Chrome, and then there's the content itself, okay? All right, back to the question. So how do I know that this is a pop-up, an actual pop-up? Is there anything else? What else could it be?
Could be an iframe.
Okay, it could be an iframe. If it were an iframe, what does that mean? Is it an actual pop-up window in that case?
No, it is inside the, it is essentially part of whatever you were originally on.
Okay, great. And actually, if you put it in an iframe, it wouldn't work from an attack perspective, but it wouldn't have to be in an iframe. It could just be the content of the page, okay? So notice that this browser window is completely contained within the website that I'm looking at, okay? So yeah, it looks like a browser window that's sitting on top, but until I move it around and try to, like, for example, drag the window above and see that its Chrome goes with it, that could actually just be an image that's on the website itself, right? And it could have a text field here, and when I type the username and password in, right, like it will type, right? It's not like a static image. It could be a bunch of JavaScript. It could even like be programmed, so if I click on this, it would pop up information about the certificate, or if I click the close button, it would disappear, right? The one thing I could not do, though, is I could not drag it outside of the content of the website, right? Because then the website doesn't control that, okay? So we call this a picture-in-picture attack because it's basically a picture of a website that looks like it, okay? So these are valid attacks. And for this reason, pop-ups have more or less gone away. Okay, now we open things in new tabs. New tabs force you to flip a tab. And so you don't have like windows hovering over other windows, generally in terms of websites itself, okay? So in this case, if I type my password in here and click on it, if this is part of the website, if this isn't an actual pop-up, it's just part of the content of the website, then the person who chose where that login button goes is the website that I'm on, okay? The outer website that I'm on. So if I land at an adversary-controlled outer website, then they can make what looks like a pop-up to a website that I recognize and trust, right? But yeah, when I type my username and password in, I'm not actually sending it to PayPal, I'm sending it to the outer website itself, okay? Now, there is one technology, by the way, that we've seen that would help you with this, which would be a password manager. So the password manager would say, oh, there's a password field, great, but it would say, well, what domain is this being sent to? Well, it's being sent to this outer domain. You don't have a password for that domain, okay? So it would never auto-populate it with PayPal because it's looking at it from an HTML perspective. And so a password manager does provide some protection against phishing and other kinds of attacks that are similar where you think you're on one website, but you're not because the password manager is actually checking for you whether it's the same website. Okay, so you tend to not see this anymore with browser windows, but there are other things that pop up over top of windows. So a lot of them would be like error messages. So you might have seen this, like you go to some shady website and you get a bunch of like messages popping up that look like it's your operating system telling you that there's some problem or you need to install. Now, in some cases, you can ask the operating system to actually display a message to the user. Okay, so sometimes that's what you're seeing is that they ask the operating system to do it. In some cases, it's just spurious. It's part of the content of the website. It's not actually something that your operating system is laying over top of the browser itself. Okay, so a lot of these problems come down to the fact that you can't always tell the difference between content and Chrome or things that the operating system is sort of putting there. And so there have been some other ideas about that, like how you address that more fundamental question. But right now it's still that case where you know, the content, especially now everything's like full screen and there's not a lot of Chrome and things like that. You can always spoof indicators that users might see. Okay, so if we drop this into our attack tree, we can use an invalid certificate. So we had a whole subtree where we could attain a valid certificate. Now it's like we could just use a certificate. It just is a wrong one. Okay, it's wrong and it's going to throw an error, but we're just going to tolerate the error because most users will click through, or enough will click through. Or there's some sort of flaw in the implementation, so the implementation doesn't notice that it's wrong. It doesn't notice that this is a site certificate signing other site certificates. It doesn't notice that this is a certificate for evil.com when the user's trying to go to google.com. Okay? There's also cryptographic attacks that I didn't cover, but for completeness, I'll throw them in the tree. Usually you don't pass around certificates, you pass around hashes of certificates. If you can find two certificates that hash to the same value, then it's kind of like getting a fake certificate. And there were older hash functions that were still supported in a lot of cryptographic libraries where it became practical to find collisions. So people found actual collisions and they were able to create fake certificates because it relied on this hash function called MD5. That's now phased out. So I think most web servers wouldn't even support it. Even if you said, I'm a computer from 1997, I haven't been updated, could you just accept my MD5 certificate anyways? Or I guess it would be the server that would be passing that to you, but I think most modern implementations would just reject it outright. If you can't get an invalid certificate, you might be able to get a revoked certificate. If you get a revoked certificate, you could just drop OCSP responses, or if they're not signed, you could try and change them. And then you could try to not get the user to even go to HTTPS in the first place. Okay, so you could do SSL stripping is that idea of every time an HTML website goes by, every link in it, you switch it from HTTPS to HTTP. You could do that like spoofing, browser Chrome thing. Another thing we didn't talk about is you can also put locks. I guess we sort of mentioned it, but you can have a website that's completely insecure. It's over HTTP, but you can put locks in lots of different places, hoping that the user thinks that because they're seeing a lock that it has to do with the fact that it's over HTTPS. So it could be in the content of the page, or it could be in what's called the favicon. So the favicon is like the icon that's here kind of thing. So you could put like a lock looking thing here, and then the user would see badssl.com with a lock icon. There's already a lock there, it just looks completely different because it's blue. But you could have like a gray lock sitting there, and then they might confuse that with the fact that they might not notice that there's no lock here because they do see the lock here. Okay, so that's one place that's a little closer to the URL where you have an image that you can control as the website owner. Okay, so if you want to look at the full attack tree, it's here. I think it's on Moodle as well as a PDF, but we kind of looked at it in smaller pieces because it's hard to fit on an entire slide. Okay, so the reason that we went through this whole exercise of looking at HTTPS was actually, it wasn't to teach you about HTTPS. What I wanted to do is I wanted to talk to you about attack trees, okay? So now that we have our attack tree and we're looking at it, what did we actually learn about the attack tree side? You learned lots about HTTPS, how it works, lots of different attacks on them. But what about the attack tree itself? Okay? So the first thing is that attack trees, unlike Stride and evaluation frameworks, you can actually go pretty deep. Like if you read that password paper that I showed you, like the actual published one, that's a very deep dive. That would take a lot of time to do. But attack trees also are like very supportive of deep dives, okay? So in order for me to explain this whole tree to you, it took, what, 3 lectures, right? Okay, so it's not, even though it's a high level methodology, right? It also can be made into a low level methodology where you actually can go into the details, okay? So it's actually something that is legitimately useful for you, okay? You might say Stride's kind of Mickey Mouse, like it's just, you know, it's high level brainstorming or whatever, but it actually is sensible. Like it's something that you might actually use. You might do a class project that's a big attack tree like this, right? And it can sustain an entire attack project, okay? Now, the next thing is, if you didn't know anything about HTTPS, could you find all the attacks in this tree? You can't, okay? So attack trees, like any security methodology, there's no shortcut where it's just like, I'm going to learn this methodology, and now I can find all these attacks that I didn't know existed, okay? It usually always works where you have to understand the thing, like just how does it work first, before you can really start thinking about the security or the attacks. Okay, so part of the reason this took 3 lectures was I was telling you also a lot about how HTTPS works. Not what the attacks were necessarily, but just how it works in general. Then when you understand how it works, then you can see what the attacks are or why they work and things like that. Okay, another thing I like about the attack tree is that you can include lots of different styles of attacks. It's not a strictly technical thing, okay? So most of this tree is technical, right? We're talking about fingerprinting or same-site scripting. You're talking about like crypto algorithms and that type of thing, right? But then you have stuff like use government laws to get a certificate from a certificate authority, right? Or just rely on users to not understand what error messages are and they just click through anyways because it's easier and they just want to get to Facebook. Or you want a certificate, just pretend you work at Microsoft. Or find someone that did work at Microsoft, pay them off, right? And then they still have their credentials or buy their credentials off them and then go in and get a certificate, okay? So attack trees don't have to be technical, okay? It's a good way where you can put the technical attacks, you can put the policy attacks, you can put the usability attacks, you can put the social engineering attacks, you can put them all in the same thing. So I just give you one thing, and this one thing covers all of the attacks. Okay, another thing is that because it's structured, it sometimes helps you see attacks that you might have missed. So an example of structure would be here under Subvert Server Authentication, we have obtain a valid certificate, use an invalid certificate, use a revoked certificate, use no certificate. And so you see that there's sort of a pattern there. It's like, okay, I can get a certificate that's valid. I could get one that's not valid. I could get one that was valid but is revoked. I could just not use a certificate at all. Maybe I didn't include it, but maybe I could use an expired certificate. So once you see that sort of pattern, it makes you think, okay, what are the other kinds of certificates? You have ones that are revoked, that are valid, that are invalid. There's no certificate. It's self-signed. It's expired, right? And then you might think of new attacks because you sort of see them all connected to each other, okay? Or here, you're like, I remember reading this article about some guy who got a certificate because he was able to go to Microsoft Mail and get SSL certificate at live.com. So I'm going to put that in my tree, okay? But once I put it in the tree, then I'm thinking, well, what was that attack really about? Well, it was about the fact that it was, certificate authorities try to figure out whether you own a domain because they send emails to you, right? Well, are there other ways that they do it? Right? And then you might say, well, I've heard of this like Let's Encrypt and they have this API thing, right? And so let me put that in the tree, and then let me think about, like, are all these attacks that work on email, are they the same, or are there new ones, or some of them don't apply to it, right? And so anyway, so once you, or here, like padding oracles, you're like, well, maybe there's other oracles like compression or bias oracles or whatever. And so anyways, when you see a couple, like 2 or 3 things that are related, it makes you think about, well, what other things are there that are related to it as well, okay? So that's the other thing that the tree helps with. You could just have a list of attacks. Here's all the attacks from start to finish, right, that we know about on HTTPS, but putting it in the tree structure where similar attacks are together in the tree helps you think about whether there's other attacks and things like that, okay? So that's why it's an attack tree rather than a list of attacks. And the idea is that the attacks, the structure of a tree should help you with the brainstorming process or help people understand what you're presenting to them. Okay, and then the last thing is is that it tells a story when you go from node to leaf. Okay, so for example, let's say that my goal is to observe HTTPS. Well, what's stopping it? Well, the tunnel doesn't end with me. So maybe I can somehow get the tunnel ended at me. But in order to get the tunnel ended at me, I would need a certificate. Well, maybe I can get away with an invalid certificate, right? So what's an example of an invalid certificate? Well, it could just be one that doesn't tie back to any certificate authority. Oh, but then the user's going to see an error. So now I'm stuck. So that attack's not going to work. Well, what if the user sees the error? Who cares? So what? They'll just click through it anyways. Boom, that's an attack. Okay? So you sort of see the story of the attack as you go from the root node to the leaf node. And every path should sort of tell its own story. Okay, so I skipped the break, I know, but that's because I knew that the lecture wasn't going to be the full length of the class. So is there any questions about any of this stuff? Yeah.
So in that specific HTTPS tree, you could again put another branch like let's say attacking the hardware.
Okay, I know sorry, I said that class is over and so everyone's stirring, but I can't hear the question.
Yeah, so like you could
5 minutes, everyone will be gone. Okay.
you can
Yeah.
create another branch where let's say you could talk about the hardware style of attacks like compromising the root, like the system and all.
Yeah.
Come up with more things, right? Not just this.
Sure. Yeah, so attack trees maybe are never complete. So again, it depends on why you're using it, right? So like in a class, it's like, well, we did 3 lectures, so we'll stop there. If you have a job and you're trying to communicate this, then you will sort of give it at the level of detail that the person wants and things like that, yeah. So attack trees, you can go as far as you want, but the idea is to be as complete as possible. So if there are entire attacks that are missing, there should be a good reason for that. You should actually try to include everything. Yeah. So in a project, if you were to do a big attack tree, then I would, if you missed a whole bunch of stuff, I would take marks off. Other questions, comments? Okay, great. So I'll see you all next week.